Okay, if we get started now. First of all, welcome to the Cambridge Cheminformatics meeting this afternoon. Welcome to everybody online as well. As you can see, we are not Andreas. Andreas couldn't be here today. So we have myself, Andrew, who are in his group, as well as Chris, acting on his behalf here today. But we'll still have a good meeting, and we'll still go to the pub afterwards. So that's good. Okay, so let's get started. Just a brief introduction on the meeting. Okay, click. First of all, next event. So this is a almost quarterly event. The next event we're currently looking at 30th November. That's provisional, but just put it in your calendar. Keep an eye on that. We have recording. So if you don't want to ask any questions or if you're not comfortable, just so you're aware, we will be recording this presentation, and all the presenters have agreed for it to be recorded as well. So it'll also be on YouTube afterwards. If you have any questions at the end, we'll go to the audience and we'll take your questions. If you have questions online, then please just log them in the Q&A box in Zoom, and we'll try and get through to you. After the talk, if you're online, please stay online. What we'll do is we'll break you out into breakout rooms. Andreas will do that virtually, so you can stay online and meet colleagues, meet up with colleagues, or meet new colleagues, etc. And here we'll be heading to the pantomimes. So please, everyone here, feel free to join us at the pantomimes. And we also want to say a special welcome to some groups from over the pond. So this is the Boston, San Francisco, and New York area group for informatics and modeling from America. So they'll be joining us, I suspect. We'll have some people from those groups joining us, so a very special welcome. And also, if you wish to present, please get in contact with us or more directly with Andreas. Also, if you just have any other information, whether it's job positions, an interesting blog you've read, something that will be interesting to the community, please get in touch with Andreas and we'll circulate it in the newsletter. And we also have to say a massive thank you to the CCDC for hosting us here today. And on behalf of the CCDC, you can see that they've got quite a lot of positions open. So please, if you're interested, we have some representatives from the CCDC here today. Feel free to get in touch. There's a lot of interesting positions here. We also have the third in silico toxicology conference coming up. So this is like the Cambridge Cheminformatics meeting, open to all, free, and also hybrid on Zoom. So yeah, if you're interested, please come along, or if you know anyone who might be interested, then please circulate this also. So we have a fascinating program today. We've got 4 talks from different areas. First up, we've got Elena from Novartis, who will be talking about local and global models for ADMET prediction. Then we've got Dan Ormsby from Dotmatics talking about adventures in AI. Then we'll have Andy Maloney from here in the CCDC giving a talk about analyzing surfaces and properties with CSD. And then lastly, we'll have a quick spotlight talk from the Skills Alliance and James Thompson. So without further ado, we'll see Elena, if you're ready to present online. And if you are able to share your screen, please do so.
Sure.
Oh.
Okay, can you see my slides?
We can see your slides and we can hear you all good. So
okay, perfect. Okay, hello everyone, thank you very much for having me here. I'm very excited today to present our work titled Systematic Evaluation, Local and Global Models for ADMET Prediction. So the drug discovery and development process involves the assessment of pharmacokinetics properties such as absorption, distribution, metabolism, excretion, and toxicity. These ADMET properties are extremely important and are usually measured using assays that can be either in vitro assay or in vivo assays. And these measurements are often costly and time-consuming procedure. So recently, it's growing interest in using in silico machine learning models that can predict ADMET properties. And this is a valid addition, especially when we need to investigate a large number of chemical structures. So at a high level, machine learning models for ADMET prediction involve a set of compounds from which we want to extract numerical representation, for instance, fingerprints or 2D descriptors, or also use the molecule in terms of a graph. And then we can use this representation in input to the machine learning model combined with the measured assays, train this model, and then predict different ADMET properties. So in this work, we analyze the difference between two main approaches for building these machine learning models that we call local and global models. So we are going to see the definitions of these models and the main advantages and disadvantages of the two approaches. Then I will present the comparison analysis that we performed, where we wanted to answer the question whether it's in general better to use a local or a global model approach. And lastly, I will introduce the diagnostic analysis where we investigated the main factors behind when it's better to use a local or a global model. But let's start with the definitions and the main advantages and disadvantages. So a local model is a model that is generated with a set of predefined compounds. These compounds can come from a specific project, a group of projects, or a chemical sequence, for example. On the other side, the global model are models that are generated with an entire set of compounds that can be very diverse. And this could include compounds that come from different projects, chemical sequence, and so on. So the idea is that we have available in the pharmaceutical industry a large amount of historical data that have been already measured for these assays. So should we use this large amount of data in order to build the models for then predict for a specific project, for example? So these two types of approaches have differences in terms of applicability domain that is basically defined by the training set. So local models are built for a very specific context. So we can think about them to be useful only if the assumption of the context are met. So for instance, we can use them we can apply them on data of the same project or the same series and so on. On the other side, the global model are meant to have higher generalization capability because they are trained on a large and diverse set of compounds. So in theory, they should be applicable to every context, so on new projects, new series, and so on. So there are several perceived advantages and disadvantages of the two approaches. The main advantage of the local model that is perceived is that they should be more representative of the specific context of interest, for instance, a project. So if I want to have prediction of data from a specific project, the idea is that I want to have a model that is built on my project data. However, there are a set of disadvantages for this approach. So first, this approach requires more effort. So we need to, every time, build a new model or test several types of models for a specific project. So this requires more frequent retraining and maintenance. Also, in projects, we often have a small size of the data set, which could lead then to the risk of overfitting. And also, it is often not possible to have a prospective evaluation, meaning that we cannot train the model with data of the past and testing on data on the more recent data, which is more in line for what happens in reality. But they are rather evaluated using the random split. So there is a high risk of generating over-optimistic results and having the same analogs in training and test sets. On the other hand, the global model, the main advantage that is perceived is that they have a higher generalization capabilities, but also from a practical point of view, these models have an easy maintenance. So once we have built a global model, we can reuse it for all the project that comes. So there is an easy maintenance, and it's also, we have available already internally global models that can be easily accessed by applications. However, one of the main disadvantages that is perceived is this large amount of diverse data in the training set might introduce noise and so not really well represent the context of interest of the specific project, for example. So in this work, we aim to answer two main questions. The first question is, if in general, is it better to use global or local model? And to test that, we performed an extensive comparison analysis for several assays. And also we asked when is it actually better to use a local or a global model. So we investigated different factors that can have an impact on difference in performance, for instance, the train set size, the structural diversity, the chemical property shift. So let's now see the comparison analysis, the setup, and the results that we got. So first of all, as a reminder, local model is a model that is generated with a set of predefined compounds. And in this work, we consider two different types of locality. The first type, we called it annotated projects. And these are projects that are manually annotated by project teams. So it's project teams that decide what compound should be in the project. And also we have the annotated series, and these are chemical series that have been manually annotated by project teams. So the machine learning setup that we used is for regression. So we aim of predicting the actual value of the assay. And the method that I'm going to explain now is applied to each project and series within each assay that we tested. So in terms of machine learning algorithms and features for the global model, we use the same approach. So we use the internal models that we have already available. So we implement the same approach, and these have been already benchmarked with several algorithms and feature sets. In terms of local model, we either implemented the approach of the global model, but we also implemented new models combining features and algorithms, mostly shallow regressors. And then we selected for the local model, the model that achieved the best performance on a calibration set. In terms of metrics, we consider different typical regression metrics. For now on, I will focus on the mean absolute error. For the validation, we use a time split that is based on the local data set. So meaning that given a project, for example, we have the compound registration date, and then we split the data set in training, calibration, and validation set according to time. So in the training set, we will have compound that has been registered later earlier in the time, and then we testing on separate calibration and validation sets. So the performance they will present from now on the separate validation set. And these also enable the direct comparison of the local and the global model because the validation set is the same. So just a quick overview of the data quantity that we have available. We tested the performance using 10 different assays. So we implemented local and global models for each of these 10 assays. And we have assays that measure solubility, permeability, clearance, and so on. And the number of molecules that we have available for these assays ranges from around 3,500 for a BSEP assay to 230,000 molecules for solubility. In terms of projects that we have annotated, we have 7 projects for BSEP to 105 for solubility. And we also, as I mentioned before, tested the same approach on the annotated series, and this goes from 24 series to 124 for solubility. So a brief overview of the performance of the global model, as I said before. So for each project, basically we are retraining a global model. So this is why in this figure you see on the y-axis the mean absolute error, and on the x-axis the different assays. So the bar represents the mean of the performance of that global model on over all the different projects that we tested, and then we have the error in terms of the standard deviation. So all the models except the cleaned assays that is built with a graph neural network are built using a standard machine learning algorithms and 2D descriptors and Morgan fingerprints. We see differences in terms of mean absolute error for the different assays that ranges from 0.33 to 0.58. And we have, for instance, for the log-D, a very large mean absolute error, but this is also the largest dynamic range that we have for assays. So that we have differences for the different assays. And we also notice that there is a larger standard deviation for the assays that have in general larger dynamic range. So in order to compare the performance across the different assays, we didn't use the mean absolute error due to this difference, but instead we use the percentage change. So to establish for each project and series the increment or decrement in performance of the local model compared to the corresponding global model and the corresponding baseline, we consider the percentage change between the mean absolute error and the local and the global, and the mean absolute error of the local and the corresponding baseline, where the baseline corresponds to the mean of the property in the train set. So as a condition for a local model to perform better of a global model, we considered an improvement over the global of at least 5 percentage point, and also an improvement over the base of at least 5 percentage point to take into account the possible random fluctuation of the performance. And if this condition is not met, we consider a global model to perform better than the local. Now I'm going to give an overview of the main results we got. So let's first look at the annotated project. So the project that were manually annotated by the project teams. So in this figure, we have on the y-axis the percentage change in the mean absolute error. So as we observed before, it's the difference between the mean absolute error of the local model and the global model divided by the global model. So if this value is positive, it indicates that the global model is performing better, and if it's negative, it means that the local model is performing better. So on the x-axis of this figure, we have the different assays, and each dot represents a project. So we colored in red the projects for which a local model approach was performing better according to our condition, and in blue, the cases for which a global model was performing better. And this dashed line corresponds to an improvement of at least more than 20% of a local model over a global one. So what we can notice in general is that for all the assays, the median of the percentage change is higher than -5%, which was our threshold, in indicating that all the global models perform better than the local model. And we also have an improvement in the median that goes from 3 percentage point up to 25 percentage point, and also this difference has been tested with the Wilcoxon-Clear test, and the results are statistically different. We also observed that there are only a few local models, just the 7% that are underlined in this box, that present an improvement of more than 20 percentage point over global models. And these are the projects for which it might be needed to expend time and effort to build a local model instead of having a global one. Then we repeated the same procedure for the annotated series. These are the chemical series that are manually defined by project teams. And also in this case, we noticed that for all the assays that we tested, so we tested just a subset in this case, except for ERG, the median, it's still, the percentage change is higher than -5%, and the global model, so we can conclude, perform better or similar to the local model. In this case, we have a smaller improvement that goes from 2 to 12 percentage point due to the compounds being more similar in the training and the test set for the local model. Also, we noticed that in this case as well, we have few local models, so only 15%, that present an improvement of more than 20 percentage point over the global model. So overall, this confirms the findings that we had before with the annotated projects. So to summarize the main findings, we observed that independently of the definition of locality that we use, the global models perform better than local models. We saw that there are only few local models that present an improvement in performance of more than 20%. And so based on these results, we see that the implementation of local models might be necessary only for very few cases. However, these cases still exist, so what we wanted to see next is whether we can identify, based on different factors, when a local model is actually needed. So now we are going to see in more details what we call diagnostic analysis, where we investigated the different factors. So this analysis is based on 645 annotated projects that comes from the different 10 assays that we have seen before. And the different factors and metrics that we consider are the following. First, we looked at the train set size, so the number of molecules in the training set. So the idea is that a larger data set of a local model should have higher performance of the global model. Also, we looked at the structural diversity that we quantified in terms of ratio of the number of scaffolds and the number of molecules in the training set. So we know that the higher diversity could hint to higher generalization capability. So this was another factor that we wanted to take in consideration to investigate reasons behind this performance. Then we looked at the shift in the chemical space, such as the distance between the train and the validation in terms of a chemical space, to see how well the training set was able to represent the validation set and how this has an impact on the performance. And also we looked at the shift in the property distribution, so to see whether the given ADMET property, for instance, solubility, was similar or different between the training and the validation set, again, to see how the representativeness of a training set could have an impact on the final performance. So let's start with the training set size. In this figure, we have on the y-axis the percentage change. In the x-axis, the training set size of the local model that at the smallest are like less than 150 compounds up to more than 2,000 compounds. So we observed that it's not a really clear trend between the local training set size and the corresponding performance. And also when we have a large set of compounds, for instance, more than 2,000 molecules, that doesn't happen frequently, the global models still perform better than the local. We see that the majority of the dots here, the projects are blue. And also in this case, we see that most of the better local models are achieving less than 20% improvement. So it might not be so worth it to spend effort in this implementation. Then, regarding the structural diversity, that I remind is the ratio between the number of scaffold and the number of molecules in the training set. We have been using from very low to high diversity of the local model. And again, in this case, we couldn't observe a clear trend between the structural diversity or the heterogeneity of the training set and the performance. So even in each of these bins, from very low to high, the percentage of projects for which a local model is better is constant. So the ratio it's of the red dots over all the dots for each bin, it's always across 20%. So there is not a clear trend. So then we looked at the shift in the chemical space, which is basically we consider in terms of difference of two vectors. We consider a signature as the average vector of 2D descriptors across a set of molecules. And so the chemical shift was quantified in terms of a Manhattan distance of the two vectors, the train set signature and the validation set signature. So for the global chemical shift, we look at the distance between the training data of the global model and the test data, which is the local model. And for the local chemical shift, similarly, we look at the distance between the training data of the local model and its validation. So what we notice in this case is that first, there is a high correlation, as we can see in the figure on the left, between the local chemical shift and the global chemical shift. However, in general, the local chemical shift is lower than the global one. And this makes sense because the data of the validation set comes from the same project of the one used for training. Instead, when we build the global chemical shift in small, medium, and high shift, we notice that the higher the shift that we have in the global chemical space, the higher the percentage of projects for which a local model perform better than global model. So meaning that when we have a large difference in the chemical space between the training set we used for the global model and what we have in the validation set, the higher is the chance that having a local model, we achieve better performance. Regarding then the shift in the property distribution, we use it, we quantified it with a Fisher ratio, and we look basically at the difference between the means and the variance of these two property distribution, and to understand how the shift in the property distribution could have an impact in the performance. We notice in this case we have a moderate correlation between the local and global property shift. But also in this case, when we bin the global property shift from a small to a high, we notice that the higher the shift in the property distribution, the higher is the chance to have a local model performing better. So basically, if we have a distribution, for instance, of solubility in our training set that is highly different from what we have in the validation set for global model, we might need to spend time and effort and create local models. So to summarize, the key findings in this analysis is that we didn't observe a clear trend between the local train set size or the structural diversity and the improvement in performance of local model over global one. Instead, what we noticed that in presence of high shift, either in terms of chemical space or in terms of property distribution, we have a higher percentage of local models that perform better than global ones. So to conclude, in this talk, we presented a systematic evaluation of local and global models for ADMET prediction. And we observed that using a large and diverse set of compounds for training can enable an improvement in performance compared to when we use a narrow local data set. So this is true independently on the locality type depth observed and across the different assays that we tested. Also, we noticed that when we have a high chemical shift or high property shift in the global model, we have more chances to have better local models. So we could now leverage the current findings in order to identify when to invest resources and then build a local models or use the one we have already available with the global ones. Before concluding, I would like to thank all people that contributed and helped during this work, especially my mentors, Gregory and Raquel. And with this, I want to thank you for your attention, and I'm very happy to take any questions.
Thanks very much, Elena. That was a very interesting presentation. Does anyone have any questions they'd like to ask?
Couple of hands.
There's a hand up from Noel in the audience. I'm just going to. Sorry, Chris first.
Thanks. This is a really nice talk. I wonder whether you consider the interpretability of the models as being a factor to consider. So when a chemist is trying to decide what to make next, is it easier to interpret a local model rather than a global model?
Okay, thank you very much for the question. We haven't looked at explicitly for now, but yeah, I think it's a very important point. So the global models for now are all, most of them are built with a standard machine learning, like a random forest or gradient boosting. And for this, it would be maybe easier to look in terms of interpretability rather than the clean assay that I said built with graph neural network. But I think, yeah, that's a very good point, and we haven't looked at it yet.
Thank you. We'll take one from Noel now.
Sure.
Thanks. I was just wondering, your last point was that the global model didn't work well if the property shifts, if there was a property shift distribution. If you turn this on its head and you select molecules for the global model which just match the property distribution, would that be a possible strategy?
I'm sorry, I didn't hear the last part of the question.
If you build a global model, not on all the molecules, but just on those that roughly match the property distribution, would that be a strategy to improve the global model?
Yeah, that could be definitely a strategy here from a practical point of view. It was also, the aim was also to look whether given the global model that are already implemented and only once, and can be reused to the different tests on the different projects. So the idea to avoid the retraining every time to build a local model, but definitely trying to observe, to consider only the molecules that are closer to the local ones could be the idea. Yeah.
Right.
Thank you.
Thank you. There are a couple of questions from the chat. The first is, did you consider, from Moritz Walter, did you consider using some form of ensemble of local and global model?
No, we didn't try that yet. I saw in literature this has been done, but again, so this could be a very good point to try. But in terms of in practice, this would require again a large amount of retraining and testing for every project that we have at disposal.
Thanks very much. And from Niels Vestkamp, nice presentation. Can you comment on what made you use a GNN only for predicting CLint? Okay,
so the strategy that have been used for the global models are the strategies that have been already used and benchmarked internally. And so after several iteration and trials for this, it was observed that for the clean assays, it was performing much better. And also it's a multitask network, so we could leverage the possibility of combining different assays for this one.
Thanks very much, Elena. Mohammed asks if the video will be uploaded to YouTube. It will be. And if Andreas will upload it and is recording it, and I'll just reach out if you want to find it. Benjamin Chittick asks, we'll take one last question. was there any correlation between MAE and whether the global or local model worked better?
Yes. Yeah, definitely. We consider of including the performance of the global model itself as one of the factors we investigated that factor as well. So one limitation it currently is that the different assays have the different range and the different performance. So we looked at the different assays, and for some of them, if there is an impact of the performance of the global model, and then percentage change, meaning that the higher the error, the higher the chance of having better local models.
Thank you.
In the interest of time, we should probably move on.
Okay.
Yeah. If you're happy to take questions, I'm sure you could answer that directly, if that's right, Elena.
Okay.
More in the chat, but yeah. Okay.
So next up, I think we've got Dan Ormsby.
Thank you very much.
So thank you very much, Elena. We'll give her another round of applause.
I just need to open it.
I now trust you to share the right screen.
All good.
All good.
Thanks very much. Take it away.
All yours. Take it away.
John.
Excellent. Thanks. Hopefully you can hear me okay. My name is Dan Ormsby. I work at Dotmatics. Dotmatics has been on something of a journey. When I joined 2008, there were 5 people. We've now got over 800 people, which is a lot more than 5. My mental adventures, I abbreviated my title as well. I had far too many slides this morning. I've chopped out many, and hopefully the message is still in here. We'll find out as I continue. During lockdown, I stopped flying. So I was going over my old expenses. In 2018, I did 200 nights in hotels, which might be too much travel. And they all stopped. And then I had a lot more time to sit and write code. So during that time, I discovered I'm awful at homeschool. I also discovered that I'm still actually, well, I think I'm quite good at writing code. And I think I can prove that in the next few slides. And I wrote 2 algorithms that are comment worthy, but even more comment worthy than that is just reminding something that everybody knows, that computers got really fast. When I finished my PhD a long time ago, the fastest computer in the world, about 2000, was hitting 7.2 teraflops. And my laptop in that bag can do 10.4 teraflops. So that's interesting, that 20 years ago, you need a 106-ton computer, and that excludes the air conditioning units, to generate, to do 7.2 teraflops. And now just your laptop does it. Even your phone is quirkily fast. It isn't quite comparable because it is FP32. So it's all small doubles, I sometimes call them. And we'll come back to that in a second. So a fast chemical similarity, define fast, is a contentious phrase. On an Amazon instance, I've got to think of a proper screen. Where'd that go away? Is that going to go away?
Bring it up and then back down.
Imagine the Zoom message going away. Oh well, never mind. On an Amazon X2 GD, it's an Amazon instance that's cheap. At Dotmatics, we host a lot of customer instances in Amazon. Amazon do, you can't see at the top, it says X2 GD. It's a cheaper Amazon instance. It costs you a couple of $1,000s a year. They're available with high memory. And into that, you can't see the URL either, but do.dotmatics.net. I'll share you the URL later. I've hosted this page. You can sketch a molecule, press run, and it will search 2 billion other molecules and give you the top sum back in about a second, 2 seconds tops. It depends on how many people are doing it at once. And that's sort of fast. That's usably fast. And I shared that with many customers. The practical use case of that is if you're in my beautiful tool called Vortex. We sell a software called Vortex. It's very nice. You can right-click a structure, punt it off to that service, and get back a list of other compounds similar to that compound very conveniently, and I can deploy that to all of my Vortex customers in one go. This is tens of thousands of users can have this button where they can press and join that into their data. And using that on a larger data set to show the practicalities of that. The example here is an assay from Kemble. The colored points have recorded PIC50s, about 150 known compounds, and you can pull into them anything that's chemically similar with this service. And then we run something called a PCA that puts points next to each other where the compounds are similar to each other, according to a fingerprint via a PCA. So if we zoom into some red dots, zooming in now, sometimes red dots are next to gray dots, and a gray dot is a purchasable compound from Enamine. Enamine's a Ukrainian vendor of compounds. They'll ship compounds to you for about $50 a time. So there's a pair of the resolution may be too small for you to see, but I've selected a couple of pairs of compounds where, say, the top compound here is extremely similar to the bottom compound, and on the bottom left there's an example with just moving a nitrogen and a CH, just swapping their positions. So if one of them was active and you had it in your project set, would you spend the $50 to go buy the thing that's extremely similar, or would you go and synthesize? Well, of course you go buy it, and you extend your lead optimization set with more real experiments by buying the compounds in from these vendors who have billions of compounds available. And also fold in AI predictions. Don't just say, I'm just doing a similarity search. Also throw some numbers on the screen from a wider view of the data to try to predict an activity at the same time. So that's really my ambition. Make the predictions of activity simple for all of my customers. I had an observation on the speed of these things, which I felt worth sharing. I'll just describe my method. In my method, I do a Tanimoto of every compound, but using a very, very short fingerprint, 128 bits. And I count the on and off bits in common. I'll show in a picture in a second. Accelerated with something called pthreads. It just allows you to use lots of cores at the same time, use all of the CPUs on your machine. And then I do a second step, which is a re-ranking with a non-folded, non-binarized fingerprint, which I also show in a picture. Looks like Ukrainian flags again, but this is 2 known drugs on the market. Top one's still under patent, bottom one's aspirin. And if you take the top fingerprint and the bottom fingerprint and look for bits in common, you get the pattern on the right. So the black ones are where it's not in common, and this gets 70 out of 128 bits that are in common across these 2. So let's compare now our query molecule, which is the top one, with the most similar thing in the billions of compounds in enamine real, and it has 111 bits in common. 111 is bigger than 70, so it is more similar according to this method. It is also the most similar compound in the enamine set, and it was most similar with this method. Just an example of that. But I don't really trust this fingerprint, and I wrote it because it's too teeny weeny, it's too tiny, it's too small. But I do take a top 10,000 or so and rescore them with something better. So I used to carry Cytologic cards long ago and used to talk about ECFP and FCFP at people. But when I joined Dotmatics, I sort of was inspired by that method and wrote my own method. And one of the outcomes is this interpretable fingerprint, as I call it, where we now have the hash of the bit, the level in the fingerprint, and then the sort of smiled fragment on the end of the thing that's responsible for that bit. So the first bit here, I've got a star and a CL on the end. That means a chlorine attached to something. The first and the fourth line are identical because there are 2 chlorines in our comparator molecule. I retain things that repeat. When you start throwing away duplicates, you're throwing away information, and that is a mistake, saying it out loud. So in this case, you do a proper Tanimoto, you got 16 bits in common. You do the Tanimoto and you get 0.16, and then the other compound where the compounds are much, much more similar, almost the same. You've swapped a chloro to a methyl, you've swapped that 3-membered ring for a, it just sends in a CH3, though it's really similar, and that gets a 0.67. It's not a percentage similar, it's just a ranking method. So trawl the billions really quick, do a re-ranking of the top N, and that's the method. I then tried it on my fancy laptop in my bag just to see how it compared with the Amazon instance, and it went faster. But you give Apple more money, and of course you'd hope it goes faster. As I added more CPUs, it stopped getting faster, about 6 CPUs, which is hitting the memory bandwidth limit of the CPU. If you look at the CPU, here's a picture of the CPU off the internet. Someone's marked it up for me. yeah, on the Graviton thing, I see about 35 gigabytes a second of RAM. That's the fastest I see it go. Amazon claim it'll go a bit faster. That's not what I see. I suspect they're doing some encryption or something to keep the things isolated. On my machine, I get 120 gigabytes a second, so it does about 7.5 billion comparisons a second. But if you look at the schematic of these modern CPUs, there's much more silicon dedicated to the GPUs than the CPUs. So let's just use the GPUs. The GPUs in these ones have, every GPU has 16 execution units. Every execution unit has 8 arithmetic logic units. That's 4,096 arithmetic logic units. Each of those can do 24 threads. That's 98,000 threads can all run at once. So that's fun. You can code it. It's not hard in something almost, I say almost C++. It's not quite C++ as I know it. There's no stdlib. There's no double. You can't just use. You can't use a double. You call it C. It's not like C if you can't use a double. That's just me being heckly though. This is a very silly example, but it's a real example. It really does run. And in this case, I would pass in 128 bits worth of fingerprint per molecule in some interarrays. That's a query in, and I would write the result into the thing, and then we can just see how fast it goes. And in my real implementation, I don't do that. I keep the top N and keep the furthest one, and I'm checking it with the next compound. And if the next compound is more similar, then I update my list. And if it isn't more similar, I go to the next compound. How fast does it go? Well, there's a tool called AsiTop on Mac you can get that shows the sort of diagnostics inside the CPU. And really, it's just this number here. So when you're doing the CPU version, 120 gigabytes a second, that's as fast as it goes. And if you do it on the GPU, it goes about 400 gigabytes a second. So of course it goes faster. And then you enter about 20 billion compounds, 20 billion comparisons a second. And I think it would go faster again, because people always want it to go faster again. You just give Apple more money. And then you can get one of the M1 Ultras instead. And I 100% believe that you'd be able, oh, what megabyte a second, gigabyte a second, 800 gigabyte a second on there. I 100% believe that it would do that 800 gigabyte a second. Yeah, so it's just how much money you give Apple. And the next M2 generation, it all goes faster again. I haven't seen the Intel chips go like this. I've touched as many as I can. There are other vendors of GPU like NVIDIA stuff that there's that first step you got to do. You got to copy everything into it first. With the Apple ones, it's all in unified memory, so you don't need to do that passing about. But this is just part of the thing. Let's call this algorithm 2. That was algorithm 2, the second best thing that I wrote during lockdown. The first best thing I wrote during lockdown was this one. So here's the beautiful Vortex again. And within Vortex, we've added a feature to allow you to train AI models, called AI, because AI is very trendy, to look for biological activities, things relevant to a successful drug profile. Of course, not all Dotmatics customers do pharmaceutical, so it applies to other areas as well. It's released within Vortex. Any Vortex customer can access it right away. It throws a dialog, say, what would you like to model? I'd like to model some columns. It will do that for you. By default, all the models have fruit-based variable names. So we see lime and peach and Djibouti Kaba. You can edit the model name if you want to call it something more sensible, like, you know, log D or something. But by default, it says jackfruit at you. And it builds models. So why do I think AI is a thing? So Dotmatics, you know, we've got lots of data for lots of customers that we host for them in our instances. Our Amazon bill in January was for 89 petabytes of data. I was looking down the Amazon bill and it sort of made me wince, and I wasn't personally paying for it. I was like, ooh, that's a lot of money going to Amazon. But that's fine, because it's across all the customers, you know, so we've got a lot of customers. And what do data scientists do all day? Well, the greenest sections here, about 80% of it, are collecting data sets, cleaning and organizing data. And that's just what the Dotmatics platform to our customers is. A lot of our customers pour data in through electronic lab notebooks, or they push robotic output at it, pushing in high throughput screening data. And we get extremely organized data, and we can make pretty views of that in the front end. So the data is super organized. It's data typed. We know what's a date. We know what's a number. We know what's a string. And it's ideally arranged for adventures in AI. So the feature engineering step is the thing you need to do to take your, well, I wrote it in this slide. Feature engineering is the process of using domain knowledge to extract features from raw data. So so really you need to do the feature engineering per domain. So if you are doing small molecules, it's a different set of feature engineering to if you're doing DNA encoded libraries. There's a different sort of domain knowledge in each of those areas. You can't take a a TensorFlow and have it just work on your data. You need to feed it some domain knowledge to let it have a clue about what a molecule is, or nothing works. So the example, of classic example, a paper from 10 years ago, doing it for images, trying to find little bits of images, shades of color that you can look for the count of and have that as an input neuron in a neural network. The frequency of a little white blob is part of the thing for, does the photo contain a cat? You know, these are the low-level features we're looking for inside images in that case to spot, in this case, faces or cars. In my small molecule world, I use circular fingerprints. So I walk around the molecule, collecting the fingerprints, just as I showed for similarity, and keeping the frequency of them. If you throw away your frequencies, you've thrown away a big chunk of your data. So if you're doing binarized fingerprints, if you're getting like a 2048 bit string, well, you've just thrown away all your frequencies in that when you folded the fingerprints together. You threw away how many fluorines there were, for example. And that really, really makes a big difference in the quality of the models that come out. So I keep bigger and bigger features, and the more higher level, the bigger the fragments get, the more unique features you observe at the same time when you're doing that. But that's all okay. And here's a really toy example, 4 input neurons. They don't really have 4 input neurons, but I have an activation function per count of the fragment. I then optimize the weights, or the code does, and we train the weights against known data during the training step. I actually have 2 to the 20 input neurons in my default setting now. So 1 million input neurons, just over, a nice round number, 2 to the 20. 1 million input neurons is my default number for the code that I did. A happy accident of that, because it all is related to a fragment in the first place, is you can run it backwards and light the molecules up according to their predictions. If you don't give medicinal chemists interpretability, you've lost every medicinal chemist. This is my hard-won experience of selling software to many medicinal chemists. That actually isn't in the release today, but I can show it working. I just haven't wrapped it up properly. I need to smooth it out a bit better. It's a bit lumpy just now, but that's details. So herd models, I moved on from the single models with my Djibouti Kaba, and I moved on to, I found just generally running many models is always better than one. It's just always better than one. So I have here on the screen the date 93, that's a single model, and the top one is an Armory 96. So I went with, so instead of fruit, because that's very silly, I went with collective nouns of animals for my model names. So that's the why the default names may look like a collective noun, because they are. And by default, I do 17 models. I can't remember why exactly I chose 17, but when you run the method now, it will go off on all the cores on your machine, running 17 models with slightly different inputs, but all the same training data to give you an aggregate of 17 models. So you have a consensus model, and you just change the number in the interface. To show it in a very practical example, if you're going to try any of this AI stuff yourself, this is what I recommend. The cheapest trick is take 3 examples. Here I have a prickle and a committee and a flock. Let's start with a prickle. The prickle is building a model on molecular weight. If you've got someone trying to sell you an AI method, if it can't predict molecular weight, walk away. Just don't go near them, because it's the easiest thing you could put, especially when the feature engineering is all fragment based. You know, you can do it with a pen and paper almost. So this gives an R squared of 0.96, but it's a small data set. Give it a much bigger data set, and you will get an R squared of 1. It will actually give you the pretty much perfect molecular weight prediction for everything in the training set. Of course, if you left out uranium and then you gave it uranium, it wouldn't get that one right, but that's okay. So yeah, so you do get that domain of applicability. And on the other end, I've got actually random numbers. So the training set on the right, it looks like you can see a line in that. You can see it's done something. So it's aligned the training set. It's called overfitting. It's aligned the training set to actually random numbers. But the left-hand side are the predictions, which of course has an R squared of 0 because they're random numbers. It's impossible to do this. But it's a good test, because when you give that to your AI vendor and they return predictions back that are accurate, you go, oh, you've been cheating. You know, so I do recommend those 2 extremes, because then in between that are the practical things. And here's an IC50. So we have an R squared of about 0.7 here, which is okay. That's kind of usable. I can live with that. One thing I didn't say is that the way I've implemented this, all these models are basically instantaneous. These, you know, computers got fast. I'll say it again, computers got really, really fast. And I do put a special comment here about how long should we train for and are we overfitting? Here's a plot of models over training steps. The bottom bit are the R-squareds of the testing set, and the top bit are the R-squareds of the training set. So we were overtraining, overfitting, but with this method, as I keep on overfitting, actually the test set flatlines and doesn't get worse. And that's just a quirk of this implementation. It was just a happy accident. It wasn't designed for that, but it's not susceptible to overfitting like some other methods. My big validation exercise, which I can talk about. So I've done other validation exercises with real customer data, but that's for them to talk about. But I'm trying to talk about the public data sets. So if you find this papyrus paper from the end of last year, they've really conveniently wrapped 60 million structures with their bioactivity data in a big zip file on Google Drive. So you can just download it and have all the data in one go. Within that data, I picked out 2,000 assays that had at least 100 compounds in each. I didn't categorize them. I didn't split them out into what was tox and what was IC. I just took everything because that's more like when I'm visiting a customer and I go into their instance, because they may have 50 projects, and on each of the projects they have 10 to 50 different parameters. And I don't know what's what, especially if it's all in Japanese. So I'll just blindly model everything and see what the correlations look like. So just like here, so I've taken all these assays. I don't really know what they are, but I'll blindly model everything and see what the quality is like. There's a lot of dense information in this plot. So if I blindly do an 80-20 split, test train split, we haven't got the dates. We can't do temporal splits here. So you just random splitting. I generated, so each of these points is the mean correlation after processing 2.5 million compounds. So many things were done here. What's happening across the bottom is I'm making the neural network bigger. So I'm starting very small, 64 input neurons. So that doesn't model so well. And on the right-hand side, it's 30-odd thousand input neurons. That models better. There's an interesting point around the middle where these lines start crossing over. The different colored lines are the depth of fingerprint. Do we take just atomic center things, how many nitrogens, how many carbons, or how many bonds are there on a carbon, or do you do bigger fragments, a carbon and its neighbors and its neighbors? So if it was in sort of cytologic pipeline pilot speak, it'd be like ECFP2, ECFP4, ECFP6, ECFP8. How wide do we go in the fingerprints? Around the middle here, the sort of 1024, that was the default size in cytologic for, well, forever. And there, ECFP2 and 4 were the winners. And there's a general rule of thumb, like ECFP2, ECFP4, they're the ones to go with if you're trying to do chemical similarity. As you go wider and wider, it turns out they're not as good as ECFP 6 and 8 and 10. So they all become the winners at the top. So in my default method now, I actually go wider again because I work with 1 million input neurons. I go ECFP 8. And on those 2,000 sets of data, it's a very dense slide. On those 2,000 sets a day, 2.5 million data points, I can do all the models and all the predictions on my laptop in 1 minute. So that's how fast computers got. That's in the CPUs, no GPUs. And that's the type of speed that I need to be able to model all the customer data that's hosted by and on-prem with customers sort of in Dotmatics instances, because there's so much data across all these. So if I want to blindly AI everything, that's the sort of performance throughput I feel I need. So that's what was done. So on the screen here are just the first 30 sets of data. It's training on the right, testing on the left in pairs. And you can see there's a line that, there's one in the middle there that's not so good, but generally the models are okay. That's sort of the conclusion. And the model knows when it's not any good. And if the model knows it's not any good, then don't publish it to any users. So one of my dreams is just to make this fully automatic, blindly model everything. And if the model is predictive, then give that out to the users. There's a bunch of other science as well I didn't go into about something I call the fun scene, the fraction of unseen features in a molecule versus the training set. That's a clue to the domain of applicability. If you throw in a molecule that's nothing like anything you've trained on, don't even bother giving a prediction. That's one of the other tricks not tricks, enterprise software features I embedded in the software. I think that's the right language. Someone in marketing told me. I spoke really quickly. I hope I didn't lose the entire audience. If you're not a native English listener, then can only apologize, but you can always catch me in the pub if you're local, and if you're not local, just ping me on LinkedIn. I'm easy to find. This is available now. It's been available since, well, for a while. This AI in Vortex, I still have them. It's all written in straight C. I have big ambitions. It'll run in everything because it's in straight C. I can put it in Excel. I can put it in an Oracle cartridge. I can put it in a module in Python. I do like working in straight C. It's happy stuff. All that Apple-y specific stuff, whilst it's fun, it's really niche to just that piece of hardware. So that's not really something. Well, I'll share it with anyone who's interested, but it's not something I'm really going to focus. I just did it because it's fun. I'm not going to. Well, that's my type of fun. I'm not going to sort of put that in I don't plan to put that in a product, but it is sort of interesting. But making a sort of general purpose fast search thing, I think is kind of useful, and I am sharing that with many customers. So if you're a Dotmatics customer, please test it on your own data, and feedback's always welcome. I think I put some thanks in, but I don't remember for which conference I wrote the thanks for. So let's see. Lucky. Oh, Viner. Well, Vinen is a great guy. He's been at Dotmatics almost as long as I have. I think he's got his 5,000 days coming up soon. So he really productizes the mess I make when I'm prototyping. He takes my elegant but fragile ideas and beats it until it can't crash anymore, which is good. I have to thank many Dotmatics customers, because it's on their data that these things really live and breathe and get interesting. And you for listening. That's a nice. Is that the end? That's the end. Good. Have I spoken so much that I can't take any questions?
No, I think we've got time. Thanks very much, Dan. That was very interesting.
I'll take questions from anyone who doesn't work for Dotmatics. Yeah.
What's your question? That's right. I'd be careful extrapolating your bandwidth figures.
Yeah.
So 300 gigabytes per second?
Yeah.
How much RAM do you have in that laptop?
That's right. So I've got, so I can load 1 billion structures.
Yeah, because 3264, I guess. So you can't. It means you can't get a MacBook with 300 gigabytes of RAM.
That's right.
Isn't it? So it's no.
But the use case is to take a customer's set of projects. So if I go to a customer nearby, they've got 50 projects, and each project is 5,000 compounds. I want to search those 5,000 times 50 compounds against, say, 20 billion for mean and mean real. So I'll load 1 billion and then search them all, then load the next billion and search them all again. So there is the loading the billion step,
right? Yeah.
There is the loading the billion step.
It doesn't quite. Again, you can't get a MacBook with 300 gigabytes of RAM. You can get a server, you can get an Amazon instance with it, but that will be.
But then you'd have the throughput, and if you buy an array of Amazon instances, they're often on the same physical machine, and then you've lost the memory bandwidth again. So, but you can buy an array of Apple machines, of course.
The other thing that was curious, is your folded fingerprint was denser than your unfolded fingerprint.
Folded fingerprint.
So you showed 100 bit set for 128, and when you showed the unfolded one, you said there was 70 bit set. So that's curious.
No. Wait a minute. No, I think I wasn't clear. No. The blue bits are the on bits.
Okay.
The yellow bits are the off bits.
Okay.
And what I'm saying is bits in common. So on in common or off in common, and that might also be called a Rogers Tanimoto. So a classical Tanimoto is on in common, whereas this is on and off in common. Because if you do on and off in common, you return an int, and you don't have any floating point at all. And that's fastest.
Yeah. Okay. So that was the total in common.
Because you're getting not just so, and this really matters.
Okay, it makes more sense. So I was like, how have you got more?
It's completely non.
That's that's clearer.
So in Vortex, if you obviously don't use it, a dialog pops up to explain this. So it really is things like if you've got a shards library. And then a load of other mess, all the shards collapse because they have so many features that don't exist together.
Yeah.
So it's like silver and gold.
That makes clearer.
Yeah. So if you've got silver and gold, they're either completely different or almost the same.
How has he got more bits?
Yeah. So it's an exclusive OR instead of a bit and.
I saw that. There you go.
That should have been obvious. So another question there's some questions on the chat. I can see them, so I'll stop sharing and I'll just leave it. On
the chat. So for the similarity ranking, did you compare your model's ranking to ranking the entire library by the normal length fingerprint?
Yeah. So the top N are always the same with the two methods. So the unless there were special corner cases, like if you're comparing a lot of molecules with very few features, like a collection of very long aliphatic chains. So if you got a load of long chains, they all look the same. So you just can't, the simple method can't see, but that's not the practical problem. So yeah, if you do the more expensive method for the whole set, you end up with the same top 10, probably the same. So that's why I re-rank the top 10,000, but only return the top 100 or 200 to hide the mess. All right, I can almost use your trackpad.
Did you do any user research or see whether the medicinal chemists found your explanations from the neural network?
Yeah, so that I haven't rolled out to real customers yet. But my other similarity stuff that does glow as well, that's always been a feature in Vortex for all time. And Vortex sells really well, so I take that signal as being it must be fine.
There is also an implementation in browser, but that's more of a fun toy.
There is, yeah. I think I've even got the video of that here. So the code is super portable. Yeah, Will wrote this, so that's why he cares. So no, not this one. Oh yeah, there's the lookup table of the collective nouns of the animals, which is very important. A candle of anteater, who knew? So yeah, the same thing. And we might not have time, but imagine a video playing. Yeah, maybe we don't have time, but there's it is having a play. Yeah. But maybe this doesn't matter. But you can run exactly the same code inside the web page. So Will very kindly did it, and it made it animate as well. So you have to make it run a lot slower to actually make it move on the screen. Otherwise, it's already finished. So, but that's just a bit of fun. It's not it's a little toy. So when you write portable C, you can pick it up and run it in something called WebAssembly, and it runs inside the web browser. It runs on your iPhone. You don't need to have to, or runs on the touchscreen of my Tesla. That was the real test. Yeah. Okay, good.
Okay, great. And I think there will take one question from the chat, I think. Mohammed asks, does your approach use index dictionary?
No.
Okay.
It makes up the fragment list from the observed fragments and the compounds every time, if that's the question.
And okay, great. Thank you.
Ping me on LinkedIn if you want a longer answer, Mohammed. That's fine.
Thanks very much, Dan. So up next, we have Andy Maloney from here, the CCDC. We'll try and get rid of the bar at the top as well this time.
Yes, thank you.
Great stuff. Thank you very much. It's nice to give a talk in front of people again. It's really good. So yeah, I'm Andy. I'm from the particle science team here at CCDC, and I'm going to talk to you about face value today. Sorry for the terrible pun. But thinking about how we can analyze and think about surfaces and properties with a new suite of software called CSD-Particle. If I can move them on a sec. Yeah, perfect. So the field here is we're not really thinking about molecules so much anymore. We're starting to think about particles and products, so formulated products, pharmaceuticals, other things like that. So at the other end of the drug development and manufacturing pipeline than where we might have thought where we were with the previous sort of talks. These approaches really, what you've got when you've got a product, you need to balance various things. You need to start thinking about your cost and your performance, of course, but the processability is important as well, because the processability impacts things like how particles stick together, how they flow, how they compact, and how they wet. Now, historically, this hasn't been a particularly digital field. It's had less people with computers and less people with white coats and more people with overalls, big boots, bigger spanners, hitting things to make things flow and work and make processes happen. But more recently, we've started to think about how we can sort of digitally transform these this area of the development pipeline. And particularly here at the CCDC, we've been thinking about how we can apply the CSD to it to sort of understand these systems and answer these questions and really get an idea of how you go from knowledge of your crystal structure, knowledge of the molecule, through to understanding your particle and the downstream process properties. So where it sits in our workflows, it certainly is, it leads on from this idea of solid form informatics. A number of you might be familiar with that already. You've probably seen talks on it before. These are sort of the normal tools that you see in the CSD materials menu in Mercury. And so that's really about understanding, using the knowledge in the CSD to understand your molecule and your solid form. But what we're thinking about now with CSD-Particle and with this idea of particle informatics is how you go from that solid form, so that nominated form that you want to take forward to manufacture. What do the particles look like for that, and what are the downstream properties? So how does it actually behave when you sort of start to smash it up and turn it into tablets? Some of you might have seen some ideas, concepts, bits of these slides before. This idea of particle informatics isn't quite new. We've been doing it for a few years now. The reference at the bottom of the page is the CSD-Particle informatics paper that we published as part of this ADOPT project. So that was a government-funded project with a number of universities. Cambridge was involved, research institutions, SMEs, and big pharma companies as well, to sort of start to think about how we do these sorts of things. Those have continued through another project, the Digital Design Accelerator platform, that's Innovate UK funded, and we've got a knowledge transfer partnership with the University of Leeds as well that's helped us to look at these things. The main things that we're looking at and thinking about are surfaces, so visualizing and analyzing properties of those surfaces. Really thinking about crystal structures in slightly different ways, so how we can identify and analyze potential slip planes and what that means for downstream processes, and thinking about how we can predict and calculate the morphologies of the shapes of the particles that we form, so the faces that are expressed. I'm not going to go into that one in too much detail in this talk, but I am going to do a little bit of revision back to sort of undergraduate chemistry, because this is a bit of an important concept to think about for later on in this. And how do crystals grow? And very, very simply, it depends on relative growth rates. So if we sort of take this center that we've got that we're growing from, we have different growth rates in different directions from that point as molecules sort of come together and you get crystals growing. The size of the relative faces that you see when faces are expressed on crystals are dependent upon those rates, and faster growing faces are smaller. So the ones that are sluggish to grow are bigger because you have faster growth in other directions, and so you get that build up along the slower growing directions there. So you can hopefully see that from that diagram there. And these growth rates are dependent on a lot of different things. So as you'd expect from the experiment that you're running, so taking the supersaturation of your system into effect, there's different solvents used, whether you've got any impurities in your system, will all affect on the growth rates of your crystals and how the shapes and the size of things that you end up with at the end. A very, very simple way of predicting morphologies is using the BFDH models. That's the Brady, Friedel, Donny, and Harker model. And it's basically just based on the unit cell. It takes the symmetry and the crystal structure into account as well. Molecules just get treated as points, so it completely ignores all chemistry, and all your growth rates are then inversely proportional to the distance between Miller planes in your unit cell. It's all right for some things. If you've got short axes, they tend to work quite well. So things with short axes tend to form these non-equant crystals that you see here. So this is like quite a plate-like crystal. It's long in some directions, it's shorter in other directions. You can sort of see how that relates to the unit cell in the diagram here. The important thing is that there are ways of visualizing, understanding the relative sizes and importance of facets in different systems. That'll become a bit more important later on. But now that we sort of have an idea of what our particles look like, we can sort of start to drill a little bit more down into the properties of them. And so we'll go into a little bit more detail as to what's in the CSD-Particle module just now. And so the first thing is the slip plane tool. And so that's really just a way of taking a crystal structure, looking at it in a slightly different way, and sort of identifying where you can find these potential slip planes and how you can analyze the hydrogen bonding network in your structures around those slip planes as well. So you can sort of see a little sneak preview of what that looks like on the screen there. This is important for when you make tablets, right? So when you take your powder, your particles that you're interested in your formulation, you squish them together to make tablets, and then you remove the pressure from your tablet press. And one of two things happens: they either elastically deform, so they just sort of spring back and don't form a tablet, or they plastically deform, where they sort of squish together, like you can see there. And so this is really relates to various structural features. You can sort of see that in some of the slides here there. But where it becomes important is when you start to think about the tensile strength and the quality of the tablets that you make from these systems as well. This is particularly important when you start thinking about combining different species together. So on the left-hand side there, you can see what happens when you squish a co-crystal together based on the individual components and sort of how that changes. Actually predicting slip planes is reasonably simple, really. What you do is you take a big slab of molecules, a cross-section of your crystal structure, oriented around one of your Miller planes, and you sort of iterate through all your Miller planes doing this, and you split that into two different slabs. You've got an upper and a lower slab, and really what you're doing here is measuring the interdigitation of one slab into the other across this mean plane. And so by identifying where you have that interdigitation, so that mesh, or where you don't have it, gives you an indication of where you might have a slip plane in your crystal structure. And so if we do this iteratively through the entire structure and look at all sorts of different Miller planes, we tend to go from 999, which is really quite high, to -9, -9, -9, which is really quite low. You can get a really good idea of how your material is going to behave and how the molecules are arranged in these slabs. It's not quite that simple, really, but because what we want to think about is the way that the molecules pack and sort of the relative arrangements, and then just finding the slip plane sometimes isn't enough. So on the left hand side here, you can see two different polymorphs of sulfomerazine, and these have different compaction properties. So as we sort of squeeze them, you can see that form 1, the black dots on the screen there, makes much stronger tablets than form 2 does. This is an aromatic molecule here, an aniline derivative on the right hand side, and you can see different polymorphs that behave in different ways as well. If we look at the actual structures from the CSD here, you can see for form 1, the one that compresses better than sulfomerazine, that's got quite clear and obvious slip planes between slabs of molecules in the structure. Form 2 doesn't have that. Okay, and you sort of see similar sorts of things for the 3 different forms of this aniline derivative as well. But the slip planes are all different. How can we actually sort of start to think about the mechanical properties from these structures, and can we actually predict mechanical properties? Well, you can to an extent, right? So you can't just think about the presence or absence of slip planes. That is really important, and that is the most important thing for these things. You also want to think about whether you've got other slip planes in your structure and where those slip planes are relative to your primary slip planes. So if you have slip planes that are sort of orthogonal to each other, I mean, really it's around about 60 degrees or so to each other, you can get some quite interesting properties. That's when you get these bendy crystals that you might have seen in the literature. So what happens, sort of happens there, is that slip planes slip over the top of each other. And that's when you sort of get these really interesting crystals you can tie knots in. That has a big effect on the mechanical properties, obviously. The separation of your equivalent slip planes is important too, and so you can analogize. You can have an analogy to this by thinking about if you try to slip thin sheets of paper across each other versus if you try to slip thicker sheets of card across each other. It's easier to slip the thicker bits of card than the thinner bits of paper, so to make them actually all slide. And that's all because the spacing between your slip planes is larger for the card. The same thing's important in crystal structures. And we want to think about the hydrogen bonding as well. It's all very well having nice clear slip planes, but if they're held together by the glue of quite strong intermolecular interactions, then there's going to be a little bit of an impediment to slip in this case. And the overall dimensionality of that hydrogen bonding is important as well. And so for the systems that we looked at earlier on, we can look at these different descriptors and see where we end up. The letters at the top correspond to the little graphics at the side there. And we can sort of see experimentally, so the observed ones is where the way that we rank these. So that's based on the slide, on the graphs from the previous slide there. And we can sort of assign a rank to these different descriptors. So the presence of a slip plane is the really important bit. That's what makes the top one there the higher ranked, the one that compresses better for the systems. It does have those slip planes where the other one doesn't. For the other example there, for the aniline derivative, you can sort of see how the distribution of those different descriptors affects the mechanical properties that you observe and that you predict from these descriptors. It's obviously not that simple. There's other things that are important, like dislocations and defects in crystals, but this does sort of seem to reproduced to give you an idea of relative rankings of the compressibility of materials for equivalent systems. So this works quite well if you're comparing different polymorphs. It doesn't work as well if you're starting to compare different multi-component systems or different systems between them each other. So the next thing to think about is this surface analysis. This is the cool, colorful bit, really, where we can simulate surfaces from our crystal structure. Be those the surfaces that we'd expect to see at the slip planes that we've just been looking at. So when they actually slip across each other, if they do or don't, what do the surfaces look like there? But equally, once we've been able to predict our particles and we know what facets are important, what do those surfaces look like themselves? And we can look at them in terms of surface chemistry, surface roughness, and surface charge. Those are some of the descriptors that we can pull out of these things. What we're actually doing here is generating slabs from our crystal structure that are based upon the facets of the surfaces that we think are important. And there's different ways that we can generate these slabs to sort of make sure that they're representative of what we'd expect to see on an atomistic level on our crystals. So you've got to suspend your disbelief in what's really going on there a little bit. But what we then do is take a probe of a certain dimension and run that across the surface. And so what we effectively produce, and what you can see here, is a van der Waals contact surface against that slab of molecules. And we can color it based on different things. So this one on the left here is colored based upon the atoms, or the interesting atoms that are there on the surface. So your hydrogen bond donors are in blue, your hydrogen bond acceptors are in red, and your aromatic groups are there in orange. So you can get an idea of what's going on at this surface quite visually, quite easily. We can calculate some descriptors based upon those surfaces as well, and so we can go for these sorts of physical descriptors and sort of think about the rugosity or the roughness of these surfaces. So that can be important for how reactive a surface is or how sticky a surface is. You can get quite nerdy about your surface descriptors and start thinking about skewness and kurtosis. But you can also think about your chemical descriptors. So we've touched on the colors on the screen there. You can also calculate the density and sort of actually get numerical descriptors out of these. And we can also generate what we can call statistically derived interaction data, which is a very fancy way of saying full interaction maps or FIMs on surfaces. So some of you might be familiar with FIMs or Superstar or Isostar. What it is really essentially is derived interaction data. So intermolecular interaction data derived from the CSD. As you can see, a full interaction map for a molecule there on the left-hand side. The blue blobs are where we'd expect to see hydrogen bond donors. The red blobs are where we'd expect to see hydrogen bond acceptors, and the browny orangey blobs that you can't see very well are where we'd expect to see hydrophobic groups. So it gives you an idea of the interaction preferences around your molecule. And historically, we've used that on a per molecule basis. So you take a molecule in isolation, you think about the intermolecular interactions that it forms in the crystal structure. You compare what you'd expect to see geometrically, so the geometric preferences for that based upon statistics based upon the intermolecular interaction data derived from the CSD, and you can kind of make an assessment of how good the hydrogen bonds are, or how good the pi stacking is in the molecule. But what you can do is you can take a surface, like I've just shown you there. These are all going to start to spin at slightly different rates. So maybe look away if you get motion sick. But you've got the same colors as we had before. So reds are hydrogen bond acceptors, blues are hydrogen bond donors. The light blue in this case, which wasn't on the previous slide, is an unsatisfied hydrogen bond donor. So because we're using the crystal structure and because we're sort of keeping things consistent with the bulk, when we generate these surfaces, we can cut hydrogen bonds to generate these surfaces that would otherwise exist in the crystal structure itself. So we highlight them in a lighter blue color to acknowledge that they are there. But anyway, if you can combine these two approaches, so rather than think about the film for the molecule itself, you think about it over the entire surface. You can see this sort of very, very colorful spinning thing on the right-hand side there. But what that's telling you, it's really what you'd probably have expected to see, is that you expect to see hydrogen bond donors near your hydrogen bond acceptors on the surfaces and vice versa. The nice thing about this, though, is that we can derive statistical data from these interaction maps. So we don't just have to look at pretty blobs of color spinning around on a screen. We can actually sort of start to drill into how dense are these blobs? How many times more likely than random are we to see an interaction occurring at a particular site. And we can start to use that information to really start to probe some quite interesting things. So a little case study on particle informatics that we've been working on involves sort of aggregated particle properties, which again is a fancy way of saying something quite simple. For each facet, we can calculate these physical and chemical descriptors that I've spoken about. And if we're able to have an idea of the relative ratios of those different facets across our particle, be that from a prediction, be that from an experimental morphology that we've obtained from a diffraction experiment or otherwise, we can aggregate them all together. So we can sort of calculate the descriptors on each surface and weight them based upon the size, the relative importance of that surface. And we can use these to answer some quite interesting questions. What I'm going to focus on is punch sticking, because I've been talking about swishing things for a little bit of this talk already. Lots of different things will determine the propensity of something to stick on a tablet press. And so punch sticking occurs in industry when you're making lots of tablets and you've got your blend and you've put it into your tablet making machine and you've got your tablet dyes and you're banging them down on this mixture and you keep doing that again and again and again. What happens is over time you can have little bits of your blend start to stick to the dye. And of course, when that starts, that sort of builds up. And eventually, what you have to do is take your machine offline and give it a clean, and that is quite irritating for industrial scientists. And so being able to understand when punch sticking will occur, for what systems it'll occur for, was going to be helpful, because it means you can modify your blend to avoid this happening, or you can understand how long you can run your process for before you need to take it offline to clean it. But obviously, that's going to be lots of different things are going to factor in that. So the humidity in the room and stuff like that is going to factor on that. Where you actually do it, whether you do it in the desert or whether you do it in the jungle, is going to have an effect on punch sticking propensity. And so we need a lot of constants in a test system. And so we picked ibuprofen because it's a nice simple drug molecule. But you'll see why we picked it again in a minute. There's a really nice paper by Debbie Hooper, who was at Pfizer at the time when she did this study on a more experimental study on punch sticking in ibuprofen. But ibuprofen, the same polymorph of ibuprofen crystallizes in different morphologies depending on the solvent that you use. So if you crystallize it from ethanol, you get this thing on this morphology on the left-hand side, this nice equine thing. If you crystallize it from ethyl acetate, you get these sort of longer lath type things. They have the same facets, but in different ratios and different surface areas. And so you've got quite a lot of controls in that test system that you can use. Now, the nice thing about it is that the one on the left sticks to the tablet press, and the one on the right doesn't really. So we've got quite a lot of systems. We can just really probe the importance of the surface descriptors quite simply for this system. And so that's what we did. So in the graphs here, you can see the blue particle, the one that sticks. So the particle that sticks is the one in blue. The one that doesn't stick is in orange. And you can sort of start to see when you start to look at the simple descriptors that we looked at earlier on. So your density of aromatics groups, your density of acceptors and of donors. You do get a bit of discrimination there. It's quite stark in terms of the density of donors. It's maybe less stark for some of the other ones there. The numbers are quite small in the densities that you're looking at. But you do seem to get a bit of a trend for the higher sticking propensity particles based on these descriptors. When it starts to get really interesting, though, is when you start to drill down a little bit deeper. And you start to look at these sort of more informatics, statistics-based approaches to thinking about these systems and looking at the full interaction maps and the densities of those. There you can see an awful lot more discrimination between the two different systems. And so I think this is quite interesting. I think we're kind of onto something a little bit here. We've got a paper that we're writing. I've been writing. It's been on my desk for a long time, and I'm rubbish at writing papers, but it'll be there soon. So CSD-Particle is available right now if you want it. So it was released as part of the 2022.2 release that came out in July. So if you've got Mercury and you've updated it and you have the relevant license, it's included in an academic license, you can play with this now, and that lets you do this the slip plane stuff, the surface analysis stuff, and it lets you do the FDH morphology prediction as well. We can do quite cool things to combine tools. So the existing informatics tools that we have at the CSD with the new tools to develop new descriptors. And these do seem to correlate some way with some downstream behavior. There's another couple of interesting case studies that some of our industrial partners have done. But there's still more research that we need to do in this, and a lot more validation with experimental data is really important, and that's all ongoing now. So thank you very much for your attention. Thank you to lots of people that did this, particularly Matt on the left there, who is now one of the 800 people at Dotmatics, and Alex, the next one in with his sidekick there, who's really done an awful lot of the work to realize this. They are finding stable walls. That's from a slightly different talk. You can ask me about that in the pub if you want to. Thank you very much.
Any questions?
Hi, Andy. Hi, Andy. Can you use
So we've not used it for solubility or melting points, but that is quite interesting. So Aurora Cruz Cabeza did some work looking at different polymorphs and sort of this idea of rugosity and how that affects crystal growth. And I think if you can sort of think about how crystals grow, you can think about how crystals don't grow, or how they dissolve, how they melt. So it's interesting. It's certainly interesting. I think the yeah. No, that'd be really interesting. I think one of the things that we're keen to explore a little bit more with certainly the surface descriptors and the full interaction maps on the surfaces is how you can think about the effect of the solvent. So you don't have to just think about simple maps like we showed you with the donor, the acceptor, the hydrophobic thing. You can start to think about the effect of different solvents. So what happens if I put a water molecule in there? What happens if I put an alcohol in there? What happens if I start to put a halogenated thing in there? And so I start to think about that. So I think there's certainly work to do there. I think that'd be really interesting. So in this case, on the surface, so sort of thinking about those surface interactions, yeah, we probably wouldn't do these in the same way with looking into the crystal structure. But, cheers.
I've never known how flat is the surface of a crystal. If I tip ping pong balls over the floor, you get that regular pattern building up, right? And you see that got a ping pong ball over here, wouldn't know there was a gap over there to go fill up. So you get, pyramids start forming. How flat really is?
It depends on the crystal, right? If you've got a really nice crystal of a metal, maybe it's quite flat, probably. With these molecular things, yeah, they're not flat, right? The surface effects do become important. I think what we've seen is the general trends that you can draw from looking at the surfaces and looking at them quickly. I think that's one of the nice things about the approach, is the speed with which you can do it. Makes it quite a nice approach. But you're right. The sort of the surface roughness, the defects, the pits on the surfaces. That's where a lot of the interesting stuff does happen. Certainly understanding how you can model them. How can we change the way that we model surfaces from being this sort of nice atomistically perfect thing to sort of start to think about those different features is really interesting. There's some really nice work being done up at the University of Manchester by Mike Anderson, the crystal grower thing that he's been developing. So that's a different way of thinking about these growth things. It kind of works backwards. If you've not seen crystal grower stuff, look at it. It's really cool. But that gives you an idea of sort of these. It gives you something a little bit more real in terms of a surface. How we could take those surfaces and apply these tools would be something really interesting. We got something similar back from the referees and mechanical properties papers. The slip planes one. It's like the compression behavior doesn't actually really come from slip planes in crystal structures. It's from defects. It's from dislocations. But I think there's been some work that's shown that the presence of potential slip planes in a structure is an indication of a higher density of those defects. And so you're, by looking for one thing, you're kind of finding something else that's helpful. But no, it's a fair point. So.
Any more questions? Yeah, go on here. Yeah, I have a question regarding short defects. So would you be able to somehow recursively predict them on average?
I'd have to think about that.
Because there's a lot of diode analysis with
Okay. Can we talk about that later?
Right, I will just see if there's anything on the there's one in the chat. The question is from Lucy Rizikova, and she asks, I would like to ask whether it was racemic ibuprofen or a pure stereoisomer used in the punch sticking experiments.
I think it was racemic. I'm gonna look at Alex and see him nod to confirm that to me. Yes, yeah, it was racemic ibuprofen for those ones.
Okay, thank you very much.
Cool, thank you.
Thanks very much. So last but not least, we've got a quick presentation now from James Thompson at the Skills Alliance. We can. Are you showing?
That's not me. So firstly, thanks everyone for having us, and thanks to Andreas to welcoming us. So my name is James Thompson. I'm the Global Head of AI and ML Drug Discovery Exec Search Practice at Skills Alliance. I'm here with my colleague Mark Damien Crosby, and he heads up our in silico practice. So just a bit of background about myself. So I actually did sort of 10, 12 years in corporate and investment banking, and left that to do something more fulfilling. So went to executive search, and yeah, I picked the area that I think personally is the most interesting. I'm sure you'll agree. AI and ML in drug discovery is a really exciting space. So yeah, that's what I'm doing now. So if just to give an overview of sort of Skills Alliance more generally. So it's founded in 2003, and we're a global life sciences search firm that covers the whole breadth of life sciences. We've got about 130 employees now and 6 offices globally. 3 of those are based in the US. We've just actually been bought out by Palatine, which is a private equity investor. So great endorsement of our business and more generally life sciences and what we're doing. And then in terms of divisions, we're split into 3 different divisions. So we've got Skills Alliance Consulting, which is more sort of RPO and top to bottom outsourcing. Then we've got the Skills Alliance Staffing, which is your sort of more individual contributor roles up to director level. And then we've got Skills Alliance Executive, which is director up to sort of C-suite and board level roles, which is what I do. So just to give a bit of an overview of the executive search practice. So in terms of how we're split and the sort of 2 groups of clients that we deal with. So biotech firms obviously helping from sort of seed stage onwards to scale those and help build out their board level positions and their executive teams. And we do that really with the help of working with VC and PE firms. So VC and PE firms, as companies, we make introductions and help the biotech firms get investment. And with each stage of investment, so when they go through the different rounds, they'll add more positions to the boards, and we'll help build those out. And then we also work the other way by taking C-suite members and executives from the biotechs that we work with and securing them board and advisory roles. In terms of the areas, so we don't, in executive search practice, we don't cover the breadth of life sciences. We just focus on the areas that have the highest growth and highest investment. Obviously, the one that you're interested in is AI and ML drug discovery. And then I've got the other areas there. So if I just hand over to my colleague, Mark Damien Crosby.
Thanks, James.
Can you talk me through staffing?
Hey guys, I'm talking to staff, and thanks everyone again for allowing us the time here to introduce and whatnot. And after a slide or two, I thought I'd try give you some benefit as to why we're here, maybe ask questions or what can we do in terms of need from a candidate perspective, or I feel like there's some hiring managers or online or offline on where or how you can overcome some of your talent difficulties at the moment. Particularly, feel free to talk to me specifically about Cheminformatics, because I have a couple of stories to share with you, both from candidate and client side, and difficulties and how to overcome the matchmaking, because I've noticed a couple of things over the last couple of months where both, I think on the candidate side, there's a unicorn objective, or trying to find people who come from very strong chemical backgrounds, but they're looking for AI ML. And likewise, it flips on the other side where clients are maybe looking specifically to have, when they ask for AI ML abilities, or someone who is able to dig deep really into deep learning models, there's a shortage in someone who has also the very high standard chemical or chemistry background that they want to see as well, in a kind of an area that I would say it does exist, but I think there's a calibration offset between both sides of the candidate client model. Very quickly, I look after the in silico side. So these are organizations that we basically deal with. So drug target discovery, molecular diagnostic companies, sequencing service providers, anyone who provides a SaaS or sequencing as a service, or pharma university and some NGOs as well. On my side over here, then this is more the wider staffing brand, so to speak, and where we specifically help our clients. So we have 5 pillars: tech data, computational sciences, where in silico fit under R&D, which you would be looking at, people like DMPK candidates, anything like that, in vitro, they would fit into that side. Manufacturing, again, once the drug or T-cell therapy is approved, when we're getting into a manufacturing stage. Commercial, everything from your marketing to anyone on the business development side. Professional services, that's more so the operational side of your organization, supply chain, procurement, anything from that aspect, your IT, the office managers, whatever it may be on that end. I wanted to, next slide is to kind of give you a success story, so to speak. Genkov, I don't know if that name rings a bell with anyone here, but basically they are within population genetics, but they've started to branch out multi-species analysis, statistical mathematical modeling, and they came to us with I think it was 9-10 months with a lot of these open on the market and unfulfilled for about 9-10 months, and having a real difficulty to actually try and identify candidates. And through a lot of combative conversations, and again, just being transparent with each other, we were able to identify people specifically across this area and successfully build out 2 seniors, a product, head of assay, and that hopefully I believe is getting close today. Good luck, Jack. They've now just opened a new lab in New York, and they're about to come up to I think their next series of funding. They've identified a couple of just recently taken on C-suite people, so they're about to go from that phase from essentially from seed, getting investment, scaling, growing, to now jumping onto an opportunity where they'll probably over the next 18 to 24 months grow in about excess of 100, 200 head. Pretty similar, should I say, to Dotmatics. So I guess the growth that they've successfully gone through.
That's a statement.
Yeah. Hopefully they'll actually bring us through that journey. On this side of the bit, this is kind of, again, we'll talk about this afterwards. I'm not going to go through everything here and go kind of through the briefs, but they're just open briefs right now here in Cambridge. There's a couple of 100% remote roles. Some are senior, some are coming straight out of anyone here who's postdoc, maybe a PhD student. Be quite happy for you guys to have a chat with me afterwards about a couple of these. I just thought I'd put up the more relevant ones for this audience today and online. Again, feel free to drop myself a message, James, or anyone on the wider in silico team through LinkedIn. Last but not least, I know we're cut for time, and we can, again, as I said, afterwards in the pub, recruiter's favorite place. I just wanted to, this may come across as like, oh, a CV, bloody hell, I know what's good and bad. You'd be surprised. I think there could be, if I had a look at people's profiles, maybe here online, there's a lot of, you're not conveying the message to your audience in how to structure. Now, this here is for a Cheminformatics role, where the company wants someone very much, as I said, with that bias of pretty deep knowledge of AI/ML. 2 candidates, same experience, both applied, and 2 very different outcomes. So over here, this is how the candidate laid out their information. No real flow. You can see date, job, specific company. It reads as 1 sentence, and it comes, it comes across as just very bland. Almost to the point is, are they actually looking for a new opportunity, or are they just having a chat? Candidate over here, you can see it's very structured from top to bottom. Name, specific department, date, title, and then they've properly laid out. And this is for the current position. In comparison to this is 3 positions, and this is over 12 years experience compared to that. Now, everyone might hear nod their head and say, well, that is, that's the way it should be. You would be astonished at how much we get of this over here. Okay. Now, the outcome of that was, this is where we kind of get involved and we coach people through what looks good, what looks bad. Necessarily, it's not always monetary based. We are here to bounce ideas off and to help you guys, whether from a hiring perspective or a candidate perspective. But that candidate there successfully got interviewed on CV when it was submitted and requested. 1st stage, 2nd stage, rejected, went back to the candidate, spoke to the client. We said, we think you're making a bad idea, actually, because this candidate is extremely good, but just not portraying that. Reformat, that candidate got the job. So it is very important so if you're looking from a hiring perspective, that necessarily doesn't mean they're the wrong talent. Okay, it's about having very open dialogue with both your parties or your third-party vendors and your internal TA team to try and convey the best message as possible and extract what the candidate actually has. Okay, and that will come through dialogue rather than this here. Okay, I'll leave it as that. But going back to, if any of these here resonate with any of you, have a chat with me afterwards. More than happy to introduce you to the relevant people on my team and to discuss them a little bit more in depth. Likewise, from a hiring perspective, Dotmatics, you can call me anytime, you get in touch if you want. And I'll hand it back over to James to close it out. But thanks a million, everyone.
Yeah, and just quickly, just to echo what Mark Damien said, is if anyone wants to get in contact, we'll send an email round with Andreas afterwards. But yeah, feel free to contact us as candidates or for people that are hiring. But yeah, we're always more than happy to help, even if it's sort of a bit of feedback on CVs or coaching, anything like that. So we're here. Thanks, guys. Any questions?
Yeah.
Anyone got any questions or?
Okay, we got one. Oh, really? Oh, for a recruiter, really?
Not so much a question, but a comment. I mean, I must get 10, 15 companies that approach me each month asking about cheminformaticians, machine learning, and things like this. And there are not enough people.
Yeah.
So my comment to them is, why don't you offer people training?
From agency point of view,
or not necessarily, or even I'm talking to the companies.
Yeah.
Why don't you, when you recruit people, you're not going to get everything you want. Select what you think is a really good candidate and offer to train them on the job.
Yeah, I think I kind of say this quite a bit. I wish there was more people like you from on the hiring end. The reality of it is, like, there is a talent shortage, particularly with this bridge of Cheminformatics, okay? Because I'll tell you from a recruitment point of view, Cheminformatics to me looks like, at the moment, what clients are looking for is, we want a data scientist, we want an AI ML engineer, and we want a computational chemist, right? That's kind of, what the brief is given to us.
Statistician.
Or a statistician, and yeah, okay. Now, 5, 3, 4 different jobs, and they don't exist, and I'd probably go to a point to say, I don't even know if that course has actually been taught in a university globally here. Now, a lot of people that we actually place successfully or eventually get there, I'm going to be honest with you, we kind of go through a lot of trials and tribulations to get to final, fail or whatnot, and eventually kind of until both parties grind each other down to find the actual reality of what you want and what the team actually needs. I think hiring managers, when there's a pain to identify or they have a pain and they want to solve it, they draw this brief up and go, that's it, that's what I want. They don't actually take a step back and communicate with cross-functionally who we're dealing with here. What is it that, you know, the AI team wants? What is it that actually the chem team wants? What is it that the person above even that wants? Like, what is the outcome here? I think that's properly communicated. You'll probably widen your talent pool, but at the moment, predominantly, they're looking for 5 people in one. Upskilling, yeah, I mean, but then, you know, Udemy, for example, a lot of people do courses on that and have upskilled, and we've had a lot of talents, but then you have a problem where clients don't validate that. So I think, you know, as much as I'd like to help the industry out and make more placements, again, I'm sitting here and you're like, yeah, but you're not, you don't, you know, you're not from a chemical background, what would you know? It's a valid point. You're more than happy to educate everyone else you do and say that too.
I can't help feeling they're being a bit short-sighted though, because your employee is going to be there for years, not just that point when you recruit them. Yeah. And so, you know, the idea of continuing education ought to be part of your decision.
Yeah. I was just going to quickly build on that. Yeah, I'll come back to you. Do you think it's the case where there are so many new companies now, new biotechs, right, that actually, if we do want to train people, you don't have anyone in-house to train them? Yeah. So in big pharma, you already have teams set up where you can do training, but maybe small, medium, you can't even do that.
Yeah, and a lot of people, like, even we had an instance, unfortunately, like this week with client and candidate, and you know, they just give them the time to get up and running. They kind of want people to come straight out of PhD postdoc, like to immediately hit the ground running in a commercial environment. And again, some people need a bit of time to kind of scale up and grow and develop. On so many companies, I agree with you. And what's happening is we want a small molecule background, or they need to have done everything in small molecule, or you'll have companies now that want to identify whatever their route to market is, where it needs to be peptide now, right? Now, as bad as it is, you want that person, but now you want them to solely have 5 years in peptide as well, in an organization that probably, I don't know if it's even, there's that many companies that have been doing that around. But again, it kind of comes back to, if you are a hiring manager or are a candidate, just make sure you're communicating the clearer message rather than this unicorn person that doesn't actually exist in a real setting.
I think to your point as well, when you're talking about newer companies, we've seen obviously within this sort of AI, ML drug discovery space, last sort of 10 years, a lot of companies have been formed. You know, you've got the big ones, Accenture, Benevolent, Recursion, those sorts of ones that have got that experience and got the people in there. And there's actually a real mix where we see people get talent from. Some are taking it out of tech, trying to pull people in from, you know, like your Googles, your Microsofts. Others have sort of more set up and, you know, have more in-house training to be able to take people out of academia and train them up and sort of shape them how they want them. But there's certainly a mix. And I think as the market matures, you know, in 10 years time, there won't be such a problem because we'll have plenty of people that have been in this space for 10 years. But at the moment, it's finding that talent that's, you know, you kind of have to source it from lots of different places. So
sit tight and be patient.
Yeah.
Cheers.
Adding to the discussion of communicating more clearly what people want in a potential hire, there was a discussion a while ago at another conference I was at, which was specifically bioinformatics focused. And the point was made that although people use the term bioinformatician, that is a very broad set of people with different specializations. So you have your genomicists, your proteomicists, your spectral resonant imaging folks. They all do very different things, have very different skill sets, but it all comes under the same umbrella term. And I think while larger companies are just saying we want a cheminformatician, what does that even mean anymore? Maybe at some point it could have been this person did a chemistry PhD or master's and then picked up computing as a hobby, but now it's something that is taught in universities, and then people go into different specializations so intensely that there's no such thing as a general cheminformatician anymore. So then you've just got to communicate exactly what kinds of jobs do you want people to do, or are you willing to, again, give them that lead time to reset what their specialism is?
Yeah, and I'll use your point right there, right? with the titles. This one here, I think that's in the web, the remote one, yeah. Where is it? This one here, an Informatics lead researcher. I would call that what they want and what they've what they've communicated. I wouldn't call it that. It's probably, I would actually call it a lead AI.
Well, similarly, principal scientist, cheminformatics brackets peptide. At that point, is that not bioinformatics?
That's not the job title. I just wanted to kind of say it was specifically within that. But
Sure.
But again, you are absolutely right. We are giving names to basically talent that maybe isn't actually that accurate.
I think we've definitely drifted into pop talk.
Sorry. Yeah. sorry. But as I said, look, guys, pick up with us. Thanks for the time.
Yeah, thanks, everyone.
We'll be in the fine. Thanks. Thanks.
Yeah, thanks very much. And to all those online, thank you for joining us. I think Andreas will be putting you into breakout rooms so you can continue to chat if you'd like. And for all of you here, we'll go to the pub. Let's go to the pub. Right.